Supplemental math videos from Circle Christian School. Parallel lines in a shape. We call them parallelograms. Those red arrowed tick marks show that the shapes can also contain parallel lines. The key here is to locate the transversal and block off the rest of the shape and see what's going on. They're pretty darn cool. Like anything in geometry, parallelograms have properties, and you need to get to know these properties to be able to solve things like different types of algebra. First, we'll look at parallelograms and their sides. Well, number one, parallelograms have opposite sides that are parallel. The second thing that a parallelogram has is congruent opposite sides. Next, they have diagonals that bisect. Bisect means cuts in half. So the middle part has a midpoint to it. And now we can do all those really great little things here of being able to set the algebra to the geometry. Geometry strategy number one, make sure you draw a picture. Geometry strategy number two, label things. What do you have to find? What are you given so that you can label the things? Well, we've been given that we have to go look for X and Y. The next thing, the properties. So I'm going to take a look at the first parallelogram here, and we have to find the X and the Y. So we have 5X and 7s and 16s and Y's. All right, well, we're just going to put the things that are congruent. So we have 5X equals 16. So I'm going to divide by the 5. So X is going to equal 3.5. And once we put it back inside, we see that they both equal 16. Now to go find the Y's. Since the sides are congruent, we just make them congruent to each other to go find the variable. And here Y equals 1. All right, that was pretty simple. I got that. So we're just going to try something that's a little bit more complex. And again, we go and look for all the properties. Hey, I have a parallelogram. Hey, I have congruent opposite sides. Hey, we can say they're congruent to each other. Beginning to sound a little bit like funsy. All right, we're just going to do the math. So first I'm going to subtract the X from both sides. Draw a little fence of equality. I did kind of skip over that. And that's going to give me X minus the 5 equals 8. That was the whole thing here. And now I'm going to add 5 to both sides. And add 5 to both sides. And look, we have that X equals 13. And if we plug it back inside, we'll see that the first one equals 21. That's our little George Polya double check. Put a 13 in here, gives me 26 minus 5, we get 21. Hey! We get the same value. Believe me, if you didn't do the math right, it would show. And last, we have diagonals that bisect. And the property is that they're congruent to each other, so we're just going to set the two congruent to each other. And you could do the math. 15x minus 12 equals 10x plus 3. Again here, you know how to do the algebra. It's finding all the great geometry properties that allow you to either have two things equal each other or two things add up to something, And a lot of times with parallelograms, it's going to be 180 degrees. So you can be my editor. Believe me, it doesn't always happen. And so I'm just kind of checking it out here too. And I'm going to add a 12. Oh, it's starting to look pretty good. 5x equals the 15. So x would equal 3. And again, I'm going to double check to make sure that I've got some good math going on here. Make sure things are equal. All right, 10 times 3 and 3 is 33. 15 minus 12, 15 times 3 is 45 minus 12. 33 also. Yay. And all's good in the parallelogram world. Parallelograms being the very cool quadrilateral that they are. They have cool angles. They have cool sides. I mean, even better than parallel lines. All right, so now we got to look at the sides. We have parallelograms. That's what the tick marks show us. And because we have parallelograms, we have things that equal each other. So we can go and find what x and what y is and what the angle of every measure is. So we have 13x equals 3x plus 100. I'm going to go minus the 3x on both sides, looking reasonable. Gives us a 10x equals 100. So x equals 10. And again, we can go find the measure. I'll put a 10 inside here. So this one's going to equal 130. I'm going to put a 10 in here for the x. And we get a 30 plus the 100. And it equals 130 degrees. Now, by right, there's a couple of ways that we can do the rest of the problems here. We could let them be equal to each other. Or we could use the fact that, hey, gee whiz, if that's 130, then we know the one down here added to the one up above equals, oh, they're supplementary. So if we put the two together, we know it should equal, this one here should equal 50 degrees, which means y should equal 2. And we can just double check again. We'll put it inside the next one here. Let's see, does that 2 work inside here? We get 8 plus the 42 gives us the 50 degrees. I don't even think I need that bottom problem to show you what's going on. Very good, but sometimes we get something like the bottom problem, and look, and our adjacent angles, when added together, does equal 180 degrees. So now I know what to do with my next problem here. I am going to add the two together because they're adjacent, one after another. I'm going to add them together. 5x plus the 10. And all that's going to equal 180 degrees. So I'm going to get a 7x plus a 40 equals 180 degrees. I'm going to go minus 40. Oh, you've already got this answer. 7x equals 140. That's one of those weird 4s that look like that with the little tent on it. And x equals 20. Throw it back inside here. Let's see, that's going to be 40 plus 30. So this one's going to be 70 degrees. Going to throw the 20 inside here. That's going to equal 110 degrees. Awesome, cool. Together they equal 180 here, and see that G equals 70 degrees. Go across here to H and see that it equals 70 degrees. Not 70 degrees, 110 degrees. Had you scared there, didn't I? And all is great in the parallelogram world. They are awesomely cool. When we get to the other quadrilaterals, we just have to, again, check out its special properties. Squares, all the sides are equal to each other. The diagonals are equal bisectors. They meet at 90 degrees, so they're perpendicular. That's going to give us cool little right triangles. The triangles in a square have that special 45, 45, 90. So they have that ratio of x times the square root of 2. You can take one of them out and deal with it, or you can take a look and notice that you have a rather larger right triangle that has a lot of the same properties going on inside here too. Rhombus is just a squished up square. It just doesn't have the 90-degree angles. So it has all the properties of a parallelogram, plus it has some right triangle properties because in the middle here, like a square, it has a 90-degree angle. So we have 4 right triangles inside there. A rectangle follows bisectors on the diagonals, 90-degree angles. So there are some right triangles inside here when you cut a rectangle in half. At least 2 congruent triangles using side, side, side. So they are very cool. Also inside here you got those vertical angles happening. So there's a congruency happening there. You just have to look at all the different properties to understand how you're going to set things up. Either you're going to add things together to equal a certain number. A lot of times it's going to be 180. Not always, but sometimes it is. Or you're going to add things together, or you're going to have things that are congruent to each other, things that equal each other. Kites are cool little things. You can kind of think of them as flying diamonds in the sky. They have 2 kinds of properties. Those that go with kites, right triangle properties because the diagonals meet at 90 degrees. And we have at least 3 different kind of congruency properties. The top outsides are congruent, the bottom outsides are congruent, and the short bisector, diagonal of the kite, is bisected in half. So you have things that are congruent, and of course you got 4 right triangles. So there's all sorts of things you can do with the right triangles. A trapezoid is a triangle with the top cut off. It might be a scalene triangle that was cut off, and the cutoff happens at parallel lines. So you have just one set of parallel lines. Maybe it was a right triangle that was cut off, and you would have a right trapezoid. So there's a 90-degree angle in it. Or the very special one, the isosceles triangle with its top cut off, is actually rather special because the bottom angles are congruent and the top angles are congruent. Now, basically, we call this base 1 and base 2. But here's the deal, all right? Either it can sit like a cup, a teacup that's been placed upside down, or you can switch it around to be the cup sitting on the saucer, which can pretty much happen with every trapezoid. It's just that naming which one is base 1 and which one is base 2 is solely dependent on you. I like making the bottom line be base 2. Your choice, though. Therefore, we have a neat little thing that happens like we do with our triangles called the mid-segment theorem of trapezoids, which basically says that if you take the bottom base and you add it to the top base, the mid-segment is going to be half as much, and that would equal the mid-segment. Same thing if you're going backwards. If what you have is the middle and one of the bases, you just fill everybody in, distribute, combine any like terms, isolate the variable, and go find out what's missing, and then double check to see if it works. All right, that is parallelograms and special quad in a nutshell. I leave it to you to find all the area formulas. Believe me, they're somewhere in your book.